Good morning, students. Welcome to SRNK Government Degree College, BANSWADA. Presented by, this is B. Narsimlu, Faculty of Physical Science, Department of Physics. So students, today we are going to learn the new topic such as Maxwell's Boltzmann energy distribution law. In this Maxwell energy distribution law, we have to discuss what is the ensemble and what are the types of the ensembles in the last class. So just we have to recall and recognize the last class. So here, so what is the ensemble is indicates? Ensemble is nothing but sum of the group of maximum number of not interaction of uniformly individual systems is called as ensemble. So here this is the diagram of the ensemble. So what is the diagram of ensemble? Here group of systems are there here. Difference. Okay, number of particles n, volume v, total energy E. Okay, this is one system. Second, third, fourth, so on and so far is there. So this sum of the group of the systems to form a big group. This is called as a ensemble. This is the concept of the ensembles. So ensembles are classified into how many types, students? Okay, three types. What are there? Microcanonical ensemble, canonical ensemble, and grand canonical. What are there? One is microcanonical ensemble. Second is canonical ensemble. Third is grand canonical ensemble. What is meant by here microcanonical ensemble? Friends, the microcanonical ensemble can be defined as the, okay, in which ensemble the energy E, in which ensemble the energy E, volume V, and number of particles n of the systems remains constant. Such type of system ensemble is called microcanonical ensembles. So what is the here main? Okay, the variables, the parameters such as the energy E, volume V, and number of particles capital N, these remains constant of any system we can take. Okay, such type of what is here ensemble is called microcanonical ensemble. So this is the diagram of microcanonical ensemble. In this microcanonical ensembles, these are the what is here one system. These are the group of systems here. This is the first group, second group, third, fourth, fifth, sixth, seventh, eighth, ninth. As like we can take the what is here this group. Okay, these groups can be what happen here, not interact with the one to another. So here in between, which walls are there here? Thermal insulated walls. These are the insulated walls. These are the insulated walls. So therefore, so according to this diagram, what we have to determine, what are the points indicates? So in this ensemble, the system does not interact with each other and with the surroundings. So it should be consist thermal insulated walls. Understood, students here? So what happened here? In this microcanonical ensembles, the each system does not interact with each other. And the first system is not interact with the second system. Why? In between they are surrounded the thermal insulated walls is the insulation means okay, the walls which can be used to does not transfer the heat energy or okay temperature or heat from one system to another system is called as insulated walls. Suppose thermoflask, simple example we can take, students. In thermoflask, what happened here? There is no heat transmitted from the okay T inside of the T of the thermoflask to the surroundings, means okay environment. So therefore the heat energy of or heat temperature of the T in thermoflask is remains constant, same is having. Okay, so therefore here also it does not interact with each system, and it is not also not interact with the surroundings. So around what is here this it has consist of what is here surroundings. So in surroundings and system also consists the what is your thermal insulated walls. That's why it does not interact with the surroundings also. So this is the main points which are considered in a microcanonical ensemble. The first microcanonical ensemble. Understood, students? Here we should remember the only 2 points. What is the microcanonical ensemble and okay, what is the main concept? Microcanonical ensemble means the energy E, volume V and number of particles remains constant. The first point. Second is okay, in this system the thermal insulated walls can be used. Thermal insulated walls can be used. Yeah, then afterwards, what is the second is? Second ensemble is yes, canonical ensemble. The second ensemble is called as the canonical ensemble. What is the canonical ensemble? In which ensemble the temperature T, okay, volume V and number of particles N of the system remains constant is called as a canonical ensemble. See here, students, very simplest. Okay, what is the definition of statement is there? Instead of the what is here? Okay, energy of the microcanonical ensemble, what we have taken here? Temperature T. This is the main constant. Temperature T we can take. Remain volume and number of particles are same. As like we can remember, we should write the what is the statement in examination properly. So therefore, understood here. What is the canonical ensemble? In which ensemble the temperature T, okay, volume V and number of particles N of the system remains constant is called as a canonical ensemble. In this canonical ensembles, what happened here? Okay, in between the we can take the what is the systems. The thermal conducted walls can be used. Which walls? Thermal, okay, conducted walls can be used here. So what is the thermal conduction? Okay, the thermal conduction means okay, the energy can the thermal energy or heat is transferred from the one system to another system is called as a thermal conducted walls here. Hence, the energy transmission is takes place, but not particles. Understand here? So this is the diagram of the what is the canonical ensemble. So in this canonical ensemble, see here, temperature T, volume V, and number of particles N. This is the one system, second, third, and so on. So far we can take okay, these are the what is here number of systems is represented by group of systems or group of ensembles is indicated by here, and okay, the vertical and horizontal lines which are there, these are the thermal conducted walls. Which was thermal conducted walls. So therefore these thermal conducted walls can be used to what happen here, the energy, heat energy or thermal energy of the what is it, any system can be, or first system can be transferred into the second system, and second system to okay, here we can take the first system as like what happened here. So and so far here the thermal energy will be transmitted in different systems. Understand here? As like we can okay, by using the canonical ensemble, the energy only transmitted but not the particles. Number of particles remains constant, volume of the system is remains constant. Understood, students? So how to this energy will be transmitted in one system to another system? Simple. For example, let us we have to take. I have given in a classroom, the students are sitting in a what is here? Okay, first desk, second, third. Okay, as like is there. I have given the book to the first student, and it will be passed to the sent to the last student. How it can he can send? He will give the what is here, that book to the behind of the student, and he will give the behind student, and so and what happened here, the book will be reaches from first to last student. How it can be okay, what is okay, reach as, isn't it any student can be moved from or okay, he can travel from first to given the last students? No, without change of the students or without motion of the students, what happened here, the book will be okay, reaches to the last person. Same similarly here, the in this the no transmission of the particles, the heat energy or energy can be transferred from one particle to another particle. To what happened here, energy can be transmitted but not a particles. Particles what happened here, at mean position it will be vibrates in all directions. It will be vibrates in what happen here? All direction. That's why it does not transfer from one place to another place. So therefore, particles are not transmitted. Only the energy will be transmitted. In where? In a canonical ensemble. That is the main concept of it. Understood, students? Another examples also we can take. Suppose we have take the what is here, one iron rod is there. What is there? One iron rod is there. This is okay. So this iron rod, when we have taken the what is A and B, so gradually when I have heated the what is here, iron rod B by using the what is here, Bunsen, what is here, heat, Bunsen burner. This is the what is here, Bunsen burner. We can take B. Immediately what happened here? The heat energy will be in this iron rod. The heat energy will be transmitted. After certain time, the heat energy will be reaches to where here? Second end. So here it become warmness. Here what happened here? Become warmness. This is the what is here? Iron rod we can take. So when we have iron rod we can take, simply what happened here? In this condition, the heat energy increases at here. How to the energy will be? Heat energy or temperature increases to the point A because of here any particles can be move? No, because of without motion of the particles, the heat is transferred from the B to here A. So in this concept, what happened here? Without motion, the thermal energy will be transmitted. So this is the main process of the process of ensemble will be takes place. So this process takes place in where? In canonical ensemble. So without motion of the particles, the heat transmitted from one system to another system. So then this is called as a heat conduction. Then afterwards, we can take the third ensemble is called grand canonical ensemble. What is the grand canonical ensemble? In which ensemble the temperature T, volume V, and here instead of number of particles we can take chemical potential. Which is the chemical potential? Mu of the system remains constant is called as a grand canonical ensemble. So here when compare the what is the canonical and grand canonical ensembles, which are here differences? Only instead of the number of particles we have take the chemical bonding. T and V remains constant. So in this ensemble, the systems are separated by thermal conducting walls. Therefore, the permittivity transmission takes place. So here this is the diagram of it. Last class we are studying. Understand, students? What is that? This is the grand canonical ensemble. In that temperature, volume, and chemical bond or chemical potential is there. So these are the groups of ensembles. So thermal conducting walls is there and horizontal and vertical. So therefore in this condition what happened here? Only the which is their permittivity of the chemical bond potential will be changes from one system to another system. Understood here? As like these are the main important what is here microcanonical, canonical and grand canonical ensembles. Understood, students? According to this, now we have to discuss the what is here topic today. Important topic is represented by the Maxwell's Boltzmann distribution law. What is the main topic here? So here we should discuss about the Maxwell Boltzmann distribution law. So here what is the energy can be distributed with respect to Maxwell's and Boltzmann, both the scientists can be determined in statistical mechanics. So now we have to derive the distribution law of the Maxwell-Boltzmann. What is the definition of it? First we have to take the definition. So here the definition of it is represented by the identical particles which are recognized in a system is called Maxwell-Boltzmann distribution law. What is the definition of the Maxwell-Boltzmann distribution law? The identical particles which are recognized in a system And in which system, okay, what happened here? The particles are identical to, we have to recognize. Okay, such type of what is here distribution law is called as a Maxwell-Boltzmann distribution. In this Maxwell-Boltzmann distribution law, let us we have to determine or obtain or recognize. We can recognize the what is here identical particles. Identical particles. So, for example, let us we can take the diagram. So, what is the diagram here? So, this is the main diagram of the Maxwell-Boltzmann distribution law. So here, what is the main concept is indicated by? So this is energy E, volume V, and number of particles N. So this is represented by the, which is the microcanonical ensemble. Which is the microcanonical ensemble. In microcanonical ensemble, energy V, volume V, and number of particles remains constant. So this is the shaded is the thermal insulated walls. That's why this is represented by the microcanonical ensembles. These are the systems. So this is the diagram of it. So let us consider the ensemble of what is here recognized identical particles. In this, each particle can be identified. Why? This is energy E, volume V, number of particles N. So in each systems, all particles we can easily identified. See, then afterwards, now let us we have take the what is here. Third is derivation of Maxwell-Boltzmann distribution law. What is the derivation of Maxwell-Boltzmann distribution law is indicates. So here let the number of particles in a system we don't know, it is represented by the small n. What we have to assume the students? Let us we have to assume the number of particles in a system is n, small n. So therefore, the particles having the what is here limited potential, limited what is here energy. That energy is indicated by the group. What is the quantum groups? That quantum groups is indicated by the what is here number of particles. That particle consists of the energy. So therefore, here we can indicate the what is here, or here we can determine the these particles divided into a quantum groups. Number of particles which are we can take. These are the what happened particles can be divided into what is here quantum groups. So therefore, the number of particles in ensemble is represented by n1, n2, n3, and so on and so forth. Ni we can take. So this corresponding number of particles in ensemble is energy, or the corresponding energy of each ensemble is represented by E1, E2, E3 dash dash Ei. These are the what is here energies of corresponding ensemble number of particles in ensemble. So therefore, the eigenstates of particles is represented by the G1, G2, G3 dash dash Gi. These are the eigenstates or eigenvalues. Therefore, the particles are consist or contain the following important properties. So according to this, what happened here? The particles are contain or consist the following properties. What are the properties or indicates? The first property is represented by the all the particles are identical and recognized. All the particles are what happened here? Identical and recognized. We can easily recognized. Second is represented by the eigenstate of ith group possess 0, 1, 2, and so on and so forth, Ni particles. The ith, what is here? The eigenstate of what is the number here? Ith group contain or possess the 0, 1, 2, 3, so on and so forth. We can take Ni particles. This is the second property of Maxwell-Boltzmann distribution law. And third is represented by therefore the particle, therefore that the number of particles in a system remains constant. What is here? Therefore, okay, the number of what is here particles in a system remains constant. That's why we can take the what is n equal to n1 plus n2 plus n3 plus dash 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 ni. We can take that n equal to sigma ni. We can write sum of this. So here the change of the it is represented by the dn is equal to sigma into dni, that equal to 0. Why? Because of n equal to constant. So when n equal to constant means dn equal to 0. So that's why we can take the dn equal to sigma dni equal to 0. This is the equation 1, students. Then the fourth is represented by the total energy of the system also constant. Which is the constant here? The total energy of the system also remains constant. So here the total energy of the system when we have taken the remains constant. So equal to what we can write here? We can write the n into E1. And it means here we can take the what is here n into E1 plus E2 plus E3 plus dash E4 plus dash 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 ni into EI. So in that n means multiplied. So we can take the what is equal to n1 E1 plus n2 E2 plus n3 E3 plus n3 n4 E4 dash dash ni EI is there. Therefore equal to we can write sigma EI into ni or sigma EI into ni we get. So when we will get the what is here this we will obtain the what is here dni is equal to change of the what we can take here change of energy dei is equal to we can write sigma. So here the change of energy dE is equal to what we can write sigma E into dni that equal to what happens 0. Why? Because of energy equal to constant, d equal to 0. Therefore d is equal to dni sigma of E into dni equal to 0. This is equation 2 is indicates. But total n number of particles arranged in n1 ways is equal to what we can write here nc n1. So therefore nc n1 equal to n factorial by n minus n1 factorial into n1 factorial. So as like students what we have to do now when we are taking the what is two equations of the number of particles we can take number of change of the number of energy will be remains constant that equals 0. Then afterwards be carefully but total n number of particles can be arranged in n1 ways. First of all we can take the n1 ways, then after n2 ways we can take, and so on so far we can take arrange that equal to what is ncr. Already you know n number of particles can be arranged in r ways is by the ncr. Ncr is the what is the formula is there according to this ncr formula. Let us we can take the what is here nc ni. So ni nc n1 ways the n particles can be arranged. That's why ncr means n into c, r is equal to n1. So nc n1 equal to n factorial by n minus n1 n minus n1 into ncr n1 equal to n factorial by n minus n1 into factorial and n1 factorial. So therefore similarly the remaining n minus n1 particles arranged in n2 ways is the remaining we can take. What is the remaining here is the remaining is represented by n1 is n1 particles is over, then afterwards the remaining is represented by the n minus n1 can be subtracted. So n1 particles can be subtracted. So the n minus n1 particles arranged in n2 ways is n minus n1c n2 we can write. That is equal to we should write n minus n1 factorial by n minus n1 minus n2 factorial whole into n2 factorial. This is the equation 4. The remaining n minus n1 minus n2 particles are arranged in n3 ways is n minus n1 minus n2 C into n3, that is equal to what we can write here, okay, n minus n1 minus n2 factorial by n minus n1 minus n2 minus n3 whole factorial into n3 factorial. This is equation 5. As like when we have taken the what is these okay 5 equations from 1 2 3, okay, or sorry, from 3 4 and 5 equations, okay, the number of particles arranged in all okay ways is represented by multiplied n factorial by n minus n1 factor into n1 factorial into n minus n1 factorial by n minus n1 minus n2 okay factor into n2 factorial n minus n1 minus n2 factorial by n minus n1 minus n2 minus n3 factor into n3 factorial. So therefore in this concept what happened here, n minus n1 factorial and n minus n1 factorial gets cancelled, n minus n1 minus n2 factorial, and this is n minus n2 minus n1 minus n2 minus okay factorial gets cancelled, and further term also gets cancelled. So we will get what is there here, n factorial by n1 factorial, n2 factorial and n3 factorial. So this is the equation 6 is indicates. So in this okay what is there, in ith group okay ni particles arranged in okay gi ways, gi means eigenstates, okay, so therefore okay let us we have to consider okay ni okay n1 n2 n3 factors. In ni factors we can take, this can be write in gy is equal to what is here, g1 equal to okay g2 okay g1 comma g2 comma g3 dash gi, okay, considered then what happened here, so y to the power of n into, or you can take the what is here, okay, if we can take the okay g to the power of n into, we can write the what is here in this concept, same gi to the power of n into g to the power of okay n2 g to the power of okay n3 and so on so far we can take gi to the power of ni. See here students, so in this group ni particles arranged in gi eigenstates is equal to gi to the power of ni. This is the main formula. But let n1 n2 n3 dash dash ni particles can be arranged or contain g1 g2 g3 dash dash gi, okay, considered eigenstates, then gi to the power of n1 okay or g1 to the power of n1 g2 to the power of n2 into g3 to the power of n3 dash dash gi to the power of ni is equal to what happened here, 7 is indicates. This is the equation 7 is indicates. From 6 and 7 equations, okay, total arrangement ways of particles is omega. So therefore omega is equal to what we can write here, ni by n1 factorial n2 factorial n3 factorial into g1 to the power of n1 factorial g to the power of n2 g to the power of n3 dash dash gi to the power of ni. So 6 and 7 when we will okay multiply, we will get the what is here, the total number of particles arranged in okay what is the number of ways. So therefore this can be right in terms of the okay following formula. What is here, omega is equal to ni into n factorial by g1 to the power of n1 by n1 factorial, separate it, g to the power of n2 by n2 factorial into g to the power of n3 by n3 factorial dash dash into dash dash, we can take gi to the power of ni by ni factorial. So therefore this can be right, omega is equal to ni factorial into pi, pi means sum of this, we can write pi into gi to the power of ni by ni factorial. This is equation 8. So here, so when we have taken the what is the equation 8, this is the number of particles can be arranged in different ways is indicates. Applying okay log okay on both sides of the equation line. So let us trace what we have to do, we can apply the log value, log okay function to above equation both sides. We will get the log omega equal to log ni okay factorial into pi into gi to the power of ni by ni factorial. So log omega is equal to log a plus b we can take, log ni factorial, pi is the sigma is indicated sum into log of gi to power of ni by ni factorial. Okay, therefore log omega is equal to log ni factorial n factorial plus sigma into log, okay, a by b, so log gi to power of ni minus, okay, log ni factorial. So we can write log omega is equal to log n factorial plus sigma into ni log gi minus log ni factorial. So, but according to, okay, Stirling approximation, the Stirling scientist has determined the mathematical, okay, approximation formula. According to that, okay, log x factorial can be right x log x minus x, x log x minus x. This is, remember students, where, okay, if you are forgot this, so we are unable to derive the equation. So this is equation 9. So when we have determined the log is applied on the what is your total, okay, particles arrangement in number of ways. Then afterwards, okay, the second concept is Stirling approximation formula can be applicable to above equation or applied to above equation. So we get log omega is equal to, see here, log x factorial, log n factorial is there. N factorial can be write n factorial, n into log n minus n plus sigma. This is the, okay, what is here, n factorial into log gi is there. So same similarly we can write ni into log gi, no factorial is there, and minus, this is a log ni factorial is there. That's why, okay, ni log ni minus ni. Okay, here no factorial is there, that's why no application of the Stirling. Where factorial is that place we can apply the Stirling approximation to, okay, we have to simplify. So log omega is equal to n log n minus n plus sigma into ni log gi minus, sigma can be multiplied inside, sigma into ni log ni plus sigma ni. So here log omega is equal to n log, okay, n minus n plus sigma ni log gi minus, here, okay, what we can take here in this concept, sigma when we take, okay, ni, okay, log ni is there, plus here n is there, and a sigma n, this n plus n and minus n gets cancelled, plus n and minus, why? Because of, we can take the what is from equation, okay, what is here, 1. So log omega is equal to n log n plus, see, sigma ni log gi minus ni log, okay, ni log n. Understood here? So therefore, okay, but, okay, n log n is equal to constant. What is the value here? N log n is always a constant. That's why, because of number of particles constant in microcanonical ensembles, okay, E, V, n remains constant. That's why n log n constant. So therefore, from maximum probability, okay, what is here? Differentiate. Therefore, what we have to do? For determination of the maximum probability, okay, differentiate the above equation. When differentiate the above equation, what happen here? So we will get, okay, with respect to ni, so differentiation of log the omega is equal to differentiation of n log n plus differentiation of sigma ni log gi minus ni log g2 log ni. So therefore this will be the constant 0 equal to 0 plus sigma d differentiation of the log, differentiation of what is here, ni into, okay, log gi minus ni, okay, log gi. This is the inside we can take. So minus sigma differentiation of what is here, ni log ni minus, okay, ni log gi minus, I have taken the common. So minus sigma into, differentiate it when the uv method, okay, dni into log ni plus, okay, ni into log ni 1 by ni into dni minus, okay, here dni into log gi. So ni gets cancelled. It's the minus sigma into log, okay, here, okay, ni minus dot into dni minus dni minus log gi into dni. So in this concept, let us we have take the what is here, okay, dni take the common. So minus sigma log ni minus log gi into dni take the common, and minus sigma dni, that equal to 0. So therefore, according to what is your equation, okay, 1, what is your sigma dni equal to 0 we can take. So minus sigma into log ni minus log gi dni minus 0 equal to 0. Therefore minus sigma into log here ni by gi into dni equal to 0. So here what is indicated? Minus, take the common here, therefore okay, we can take the sigma log ni by gi into dni equal to 0. This is the equation 10 is indicates. Now but from the Lagrangian undetermined coefficient, okay, multiply equation, okay, 1 with alpha and 2 with beta and add to these values to the equation 10. What is the main concept, students, here? According to Lagrangian, okay, undetermined, okay, coefficients, here third concept is done. This it should be remembered. Okay, when okay, we have to apply the what is the Lagrangian undetermined coefficient. Okay, so simple. The equation 1 and 2 multiply with alpha and beta values, and these okay values can be added to the equation 10. So what is the first, okay, according that, so sigma log ni by gi into dni plus alpha into sigma dni, first equation sigma dni, plus beta into sigma ei into dni, that equal to 0. So you go, here we will add the what is alpha to the first equation, beta to the second equation. Say okay, we will get the what is here these values to add the what is the equation 10. So we will get the what is the equation here. This is a okay simplified. So this equation can be simplified. We will get sigma dni, okay, see here sigma dni, sigma dni, sigma dni is there, that's why sigma dni take the common log ni by gi plus alpha plus beta ei equal to 0. So but sigma dni not equal to 0. When it becomes 0, what happened here? Everything becomes 0, no change of the particles. That's why okay, this is does not equal 0. Its coefficient okay is become 0. So that coefficient is log ni by gi plus alpha plus beta ei is equal to 0. So log ni by gi is equal to minus of alpha plus beta ei. So here ni by, therefore ni by gi equal to, we can write e to the power of minus alpha plus beta ei. So ni by gi is equal to what we can write here? So 1 by this e to the power of minus, they take downward, 1 by e to the power of alpha plus beta ei. So therefore we can write ni is equal to gi, take this side, okay, gi by e to the power of alpha plus beta ei. This is the equation 11. This equation is called Maxwell's Boltzmann distribution law. What is the Maxwell-Boltzmann distribution law? Ni equal to gi by e to the power of alpha plus beta ei. Okay, where ni is the number of particles of ith particle, this is the gi is the ith eigenstate values, and here alpha beta are constants, and ei is the ith energy of the okay particle. So this is the what is the main important okay, what is the Maxwell-Boltzmann distribution law. So this is a very very important okay, what is here concept for the PG examination. So students, you have to okay, once again you have to practice it. When you went to the home, practice it. Okay, then okay, without seeing, you can write down the derive the what is this equation. So we will get okay very easiest way. So we have to, where the concepts are there, that concepts or applications can be applied to simplify this equation. Okay, so thank you so much students. Okay, thank you one and all. So